Thank you very much, Glenn, and everybody. It's a pleasure to be with you. We'll take you through some ancient history of the creation of the Arpanet, which then led into the full-scale expansion of the internet. I have another engagement, unfortunately, at the top of the hour, so I'm going to have to hold it to precisely that. I'm going to try to leave, as Glenn suggested, 10, 15 minutes after my slides and my talk for open questions, which I'll be delighted to engage with. Next slide, please. So I'm going to talk about, as I said, ancient history, 50 years or more ago, about the Arpanet, and some comments both about what the context and perspective was back then, and a few comments, nothing super deep, but a few comments from today's perspective, looking back and perhaps with application to the future. Next slide, please. So here's the timeline for the Arpanet. The first IMP was installed in September 1969. There was, as you would expect, a period before that where there was a lot of thought, first in general form and then more specific, and then finally a very specific plan that then led to the development of the first IMP. The IMPs are what we called routers, or that is, we didn't have the term in that day, in those days, and so, but that was what an IMP was. It was the first router. First one was installed at UCLA, and in the several months prior to that was the design and implementation, and in the many months and before that was the thought process. There was a lengthy period, well, it seemed lengthy at the time, it looked short in retrospect, of expansion, use, and maturation of the Arpanet itself, and then research on other technologies, particularly packet radio and packet satellites, and how to interconnect multiple independent networks, which is what the internet's all about. In 1983, marked a major transition point, the transition to TCP/IP, the splitting of the Arpanet into two parts. One was the continuation of the sort of academic and research-oriented part, and the other was for the use by the military for their purposes. And that also marked the beginning of the internet, per se. And then finally, several years later, the last pieces of the original internet were, the original Arpanet were turned off. Next slide, please. A few words just to place, where I was in the picture. I had been an undergraduate at UCLA. I'd spent a lot of time programming. That's a polite way of saying I didn't spend much time on classes. I spent lots more time hanging around computers, and both for education and for profit, put myself through school. Excuse me. I went off to MIT briefly for graduate school, came back to UCLA. The Arpanet project was starting. My research interests were off in a different direction, but this seemed like a useful project. I wasn't sure that it had the intellectual depth of what I had been in my youthful arrogance, thinking what was stuff that really mattered. But I thought, well, I'm pretty good at this stuff. I can lend a hand. I got deeply involved, led the network working group, created the request for comment series. I had, over the years since then, done a lot of research in formal methods, network security, and so forth. And then eventually was the first area director for security in the ITF. And then about 20 years ago, got involved with ICANN, chairing their Security and Stability Advisory Committee, getting on the board of directors, and eventually becoming chairman of the board for the last 6.5 years of my tenure, ending about 3 years ago, ending closer to 4 years ago now. Next slide, please. All right, so let's go back and look at the Arpanet in more detail. Next slide. I'm going to make some minor comments along the way, and here's a very, very big, broad thought that if you look at sort of what the pivotal points are and when decisions get made and how things play out, I think it's helpful to think in terms of three things. One is the technology's been improving, and we've been all riding that wave, and I'll show you a few details of that. That's been huge. On the other hand, we have continued to be the same human beings that we were, for good or bad, and our human nature doesn't change much. And then there should be a smiley face next to that. every once in a while, good luck helps, and one just benefits from that. Next slide. All right, from the mid-'60s to the early '70s. Next slide. Let me take you back to what computing looked like in the mid and late 1960s, even the early 1960s. Most computers were expensive and not widely distributed. You found them in important places, universities, governments, big businesses, and so forth. And they were mainly used in a batch processing mode of keeping them busy doing important work. That is, not wasting time interactively supporting the humans, but as I say, doing important things. And they were typically, well, many of them were big machines that took up a whole room with a false floor and air conditioning and so-called mainframes. But there were places, notably around MIT, but also in other places that were focused on, well, what happens if you change the perspective and think of computers as supporting interactive work so that it facilitates what humans want to do. That led to both small machines as personal machines eventually, but laboratory machines, but also big machines used in a time-sharing sense where you had many, many people, many in those days it was like 30 to 50, not thousands, sharing one mainframe that would slice up its time and give a little bit of time to each one and give the impression that you were using the machine yourself. There were also focus on graphics, on man-machine interaction, on artificial intelligence research, and a lot of this came from one particular funding agency in the government, in the U.S. government, which was ARPA, later renamed DARPA. Next slide. So let me tell you just a moment about ARPA or DARPA, a well-known story, but worth mentioning. Inside the U.S. government, and in particular inside the U.S. Defense Department, there had been multiple efforts to build a space program. You had the Army had a program, and the Navy had a program, and they were competing and not getting very far. And then the Russians put up the first satellite, and that sent a shockwave through the U.S. government. In relatively short order, measured in a couple of months, the U.S. Department of Defense created a new agency that was outside of the Army, Navy, or Air Force, but inside the Department of Defense, plugged in at the very top to prevent technological surprise, and focused heavily initially on the space program and then on to other things. Next slide. And that was, and when that agency was created, it was created as a sort of lightweight agency within the Office of Secretary of Defense. The term Office of Secretary of Defense might bring to mind a picture of, one person, the Secretary of Defense, and one support person, the Secretary or Administrator. Actually, the Office of Secretary of Defense is a couple thousand people. And the agency that was created was about 150 people. Small potatoes in terms of large bureaucracy, but nonetheless not a tiny little operation. In 1972, it was moved out of the Office of Secretary of Defense to become a separate defense agency and renamed DARPA, so it acquired the initial D. Didn't mean any change at all of significance. And then 20 years later, under Bill Clinton, taking advantage of the fact that a lot of what ARPA had actually accomplished was not only useful for the military, but useful for civilian use as well. They wanted to emphasize the dual use and change the name back to ARPA. That lasted only a few years, then it was renamed back to DARPA. So you'll hear me say ARPA because that's the period that I was involved in. I spent a few years in that agency, and that's where the term Arpanet comes from. But since 1972, and with the exception of those few years, it's been DARPA, and so that's the way most people would refer to the agency. Next slide. Within the agency, there were a handful of separate offices, each focused on different technologies. The Information Processing Techniques Office wasn't one of the original parts of ARPA, but after ARPA had been started for a few years, this office was created to focus on long-term research related to computer science. And the strategy was to invest heavily in a handful of centers of excellence: MIT, Carnegie Mellon University, Stanford University, Berkeley, and some others, including even non-university places, and to really push the envelope with respect to supporting man-machine interaction in a variety of different ways. Time sharing, as I mentioned, AI, artificial advanced graphics, new architectures, and then, not incidentally, various attempts at trying to connect computers together. Next slide. So before the Arpanet project was started, what was the state of networking? Well, there had been some successes in connecting computers together in special purpose networks, both in the military and in business. So American Airlines had a reservation system called Sabre. Then there were some special purpose military networks that were connected. These were typically controlled in their architecture in that they had the same kind of computers used everywhere, and they were used in a very narrow and specific sense. The Arpanet project was initiated in an environment where they already had major research programs going in several different places, as I said, and there was quite a bit of variety in the computers that were there and in the kind of research that was being done. And so this form of interconnecting these computers pressed the limits on what was known, or tread, if you will, into the unknown regions. How do you connect a bunch of different kinds of computers? And the other most important and salient fact was that the focus was on interactivity. It's quite a different matter if you want to connect a bunch of computers together with the purpose of moving mass amounts of data efficiently and keeping the circuits busy. It's if you want to support interactive computing, then you've got a different kind of problem technically, because the way people interact, they don't tend to keep the lines full. And I'll show you a bit more about that in a second. Next slide. So then the Arpanet project starts. Next slide. And the initial footprint of the Arpanet consisted of 4 sites: UCLA in Los Angeles, University of California, Santa Barbara, about 100 odd miles north along the coast of California. SRI used to be called Stanford Research International, and along the way it got renamed, in Menlo Park, California, a little bit south of San Francisco, and then the University of Utah in Salt Lake City, Utah. And the initial network, pictured here, the famous diagram that's been used many, many times. The round circles are the routers. As I said, we call those imps, and the rectangular boxes are the computers that we used, and each of them was used in time-sharing mode. Excuse me, and interactively. And the critical part of the design of the Arpanet was that it would use packet switching as opposed to circuit switching. That means that what was sent from one host computer to another was broken up into small chunks, and then those chunks were sent into the routers, into the IMPs, which then forwarded them and shared the lines as need be. But the goal was to use these lines much more efficiently without losing a significant amount of the interactivity, as if you had the circuit to yourself. Next slide. So I want to just emphasize again that the focus here was on how to support research in these places, how to connect people together, how to press the envelope of what was known about how to do this, create the technology, and take a very long view about the transitions that were being made in both computing and communications. There's been a lot of discussion about, well, it used packet switching, and it would find ways to route around breakages, so it must have been for nuclear survivability. The story is actually a bit more complicated, but the main answer is that was not the primary goal, or even a direct goal of the Arpanet project itself. There were some words that if this technology matured, it might be useful in the future for future systems that could be based on that. which is all fine and correct, but the project itself didn't spend any time worrying about that sort of recovery from outages. It did spend time on what do you do if an imp breaks or what do you do if a line breaks. But that's a different, qualitatively different problem than trying to address nuclear survivability, which is a huge, messy, terrible problem that, as best I can tell, the strongest answer is we just hope we never get there. Next slide. This is a picture of what the imp looked like. That's about as tall as a person. It's like a small refrigerator. The original imps, of which this was one, were put in heavy-duty metal cases because they were being put in a very hostile environment, that is, universities. And the people who designed this were worried about what the students might do. After some number of these were built at the cost of $100,000 in 1969 dollars, they backed off and built ones at about half the price that worked just as well. Each one of these was capable of being connected to 3 or 4 computers locally. Locally started out to be 50 feet, and then there were extensions to that. But this was before the creation of local area network technology like Ethernet. And so you had small clusters of machines, but not the huge numbers. And indeed, in those days, we didn't have personal computers. We didn't have workstations. They were a little bit in the future. Next slide. So a bit more about packet switching versus circuit switching. On the left, well, on the right, let me start there. When you make a phone call, it typically takes several seconds to initiate the call. And if you're using it for interactive data communication, the amount of data that you're actually putting on the line compared to the amount of time that it's there is a very, very small fraction of the total, typically on the order of 1% or less. Now, on the other hand, you get the benefit of no jitter, and the delay is quite fixed. The speed of light in free space is about 5 microseconds per mile. In wires, it's about half that speed. And on the other hand, in packet switching, the setup time goes away because you can just send right away and it goes. And you can drive the efficiency of the use of lines up into the 50 to 70% range before you start getting queuing delays, and you can go a little bit further if you really push it. You do get some variable jitter in terms of when things arrive compared to when they were sent, and you incur some delays as you go through each hop. Plus, you get the speed of light transmission as well. So there's your trade-off, and if you can live with those, which you can for a surprisingly wide range of applications, then packet switching is a huge, huge financial advantage in terms of the use of relatively expensive, no, very expensive communication lines. Next slide. So here's the timeline that is a little bit more fine-grained than what I talked about at the outset. There was a design period, roughly 66 to 68, and then finally a request for quotations was sent out from the government to build the IMPs and have them installed. And most of the focus up to that point had been on the topology of the network and on the cost of the communication lines and the efficiency and so forth. Not a whole lot of attention on what the hosts were actually going to say to each other and how they were going to do that. Then in August of 1968, with the request for quotes already released by the government, there was a meeting that turned out to be important for a certain number of us to get together and think about what we were going to say to each other over this network. As it happened, both Vint Cerf and I were grad students at UCLA. The meeting was held at Santa Barbara, chaired by Elmer Shapiro from SRI. And so several of us, on the order of a dozen people, gathered in a room to chat for a day and a half about how this was going to go. It was pretty much of an open, uncharted territory, and we made only one big decision that day, which was that we needed to keep talking to each other, and that to do that, we should start visiting each other's laboratories and get a sense of what the environments were. And there was a certain note of irony that we knew that this network was supposed to support cooperation at a distance without the need for travel, and the first thing we did was increase our travel budgets enormously. But compared to today's, or pre-pandemic anyway, travel, that was tiny, small potatoes measured in hundreds of dollars instead of in tens of thousands of dollars. Bolt, Brannick, and Newman in Cambridge, Massachusetts won the bid for building the IMPs, and they started formally on January '69. Meanwhile, our little group continued to meet, and after several months, decided we better write down some of the thoughts that we've been kicking around. And so in April 1969, we kicked off an informal set of notes with some trepidation that they might be misinterpreted as asserting authority or putting ourselves in a position that we didn't belong in, because there was no formal charter, there was no formal governance structure or anything. And I had the pen at that point, and I said, well, let's use the term that Bill Duvall had suggested as requests for comments as a way of saying these are informal and they're intended to stimulate discussion, not cut them off. I expected it to be a short-lived series of notes, 6 months, maybe a year, and then there'd be formal notes. I also expected people who actually knew what they were doing to come along and take control. Neither of those things happened, and the RFCs continue to this day, although with some important transformations, because in those days, we had no way of communicating them except by sending them out by U.S. mail to each other. Nowadays, of course, we have email and we have internet drafts, and so the RFCs are transformed. In any case, in very short order, Bolt, Brannick, and Newman did a stellar job, delivered the first game to UCLA in beginning of September '69, the second one to SRI beginning of October '69, and monthly after that, pretty much. Next slide. Here's what the network looked like in June of 1970, so it's 9 months, basically, 8-9 months after the first delivery, less than that, I guess 7-8 months after the delivery of the first IMP. Note that there's a concentration in the Southern California area, but there's also now 2 cross-country lines and a collection of sites in the Boston area, MIT, Bolt, Brannick, and Newman, and Harvard, with Utah sitting there in the western part of the U.S. Next slide. 7 years later, we stopped drawing the network using the geographic map because there's just too many things to fit on, and this gives a sense of what that growth looks like. Let me also emphasize, back up one slide if you will, that the lines that we were using in those days were somewhat peculiar by today's technology. They were fundamentally analog lines, 12 voice grade lines that were bonded together to create a 50,000 bit per second, not 56 the way you would use today, but 50,000 bit per second communication. And the modem that did all of this was a relatively humongous piece of equipment that was, each one of the modems was sort of the size of a bread box, and they fit into a cabinet sitting next to the IMP, about half the size of that IMP. Today, a so-called voice grade line can carry 56,000 bits digitally, and of course we have much faster lines. We moved from kilobits to megabits to gigabits over a long period of time. But in those days, this was considered super fast. It wasn't fast for the kinds of applications that we would do today. Sending video, having interactive session as we are having right this minute was in the future. It was stuff that we understood and stuff that we hungered for. There were some preliminary experiments, but it was a long time before we could do what we're doing at this very minute. Next slide, and the one after. So the game plan, if you will, for building the Arpanet was, as I said, to connect the existing research sites. And this had some very strong benefits and also colored the work quite a bit. There was a lot of cheap labor available at these sites. That is, people like Vint and me, who were graduate students, and we were on graduate student stipends. And we were not to brag at all, but we were decently good at programming and designing things, more or less the equivalent of commercially professional people. And it wasn't just us at UCLA, but it was true across the board. These were cutting-edge research sites and attracted another key thing that came out of the project was the all-important decision to separate the routing from the host computers. Instead of just connecting the host computers directly to each other, they're connected through these routers. It is absolutely what's done today everywhere. Nobody thinks twice about it, but it was a non-trivial decision, particularly because computers were so expensive that the idea of having you're going to put another computer at every place, how much is that going to cost? And so, but also prices were dropping at a rate that made it feasible. Further, the U.S. government had access to buying these circuits or leasing these circuits at a price that was qualitatively less than if we tried to do it commercially. So we used the routers that were built and the communication lines, the routers from Bolt Brannick Newman, the communication lines from AT&T, and then left open how the protocols were going to be defined. There wasn't actually a top-level concern going in, but there was a sense of, well, we'll figure it out as we go. Next slide. There had been a kind of kitchen cabinet that Larry Roberts, who was in charge of IPTO, used that worked with him in the initial period of choosing the first 4 sites and the basic outline of the network. Next slide. And then us kids got involved, and we started to think about, okay, how are we going to get involved in this? The main thing that we brought to the party, if you will, is that we had, as I said, a lot of experience in designing operating systems, programming language, and building systems and so forth. And so with that mindset, we were able to view the ARPANET from both the perspective of what could we do, and also how would the users, and when we talked about the users, we were really talking about people like us. What did we want it to look like for the kinds of things that we wanted to do? Next slide. After a bit of thought, we settled on using the idea of a virtual circuit as a building block. It wasn't the solution to everything, but it was a useful idea as a piece of architecture, and that would hide the details of the packet switching. So even though the packet switching was crucial in terms of making efficient use of the communications that was being provided, we then overlaid that with a way of hiding that that's what was going on, and said, okay, now imagine that you've got a virtual circuit between any 2 points. Can you build the things that you want to build on top of that? In particular, the obvious applications were remote interaction, as if you had dialed up with a terminal. And the other, of course, is moving files. For one, you want to say, take this file and move it and put it over there. Both of those are workhorses even today, but they were the principal focus. But we equally wanted not to be limited to just those 2 applications. Next slide. So actually, I'm sorry, back up 1 slide. So the last point is one that I should emphasize. We wanted the framework to open and permit more general forms of intercomputer interaction. That was uppermost in our mind, even though we knew that the file transfer and what became the Telnet protocol would be dominant to start with. And one of the things that we thought about was, well, these 50 kilobit lines are fast, but they're not as fast as we'd like them to be. There's a lot of interaction that takes place that you want to be very, very quick and lively. And so we came up with the idea of possibly at the beginning of a session, you might download a small program that could be interpreted locally that would take care of easy interaction. So if you were typing a command, for example, and you wanted to erase a character, maybe that could happen locally, and you wouldn't have to forward those characters back and forth across the entire network. That was a very powerful idea. It didn't get fully implemented until about 25 years later with the appearance of ActiveX and then Java and now RESTful interfaces. But it was one of the things that that we, as I say, we thought about and actually did some paper designs and a little bit of implementation at the outset. Now the next slide, please. So focusing on what we call very blandly the host-host protocol that created a virtual circuit. At first it seemed pretty easy, and then a couple of important factors became visible to us. One was, well, you don't want to just allow the sending side to send arbitrarily. You want the receiving side to be able to have some control as to whether it's going to be overrun. And so we created the notion of flow control. As it turns out, flow control is harder than it looks, and it's multi-layered. The imps themselves also engaged in flow control, but their flow control took care of their needs to not have their buffers be overrun. But we also realized that hosts needed to have a similar sort of thing. So you got multi-layers of flow control there. We didn't know how to do it very well. We didn't know what the parameters ought to be. We didn't even know whether we wanted to measure the bits or the number of messages, the packets being sent. And we settled somewhat awkwardly on measuring both and providing the receiving side with controls on both how much space was available and how many messages it was willing to handle. The next thing we discovered was that, for interactive sessions, sometimes you are dealing with a program that's run away. You need to hit an interrupt character. The interrupt character, dependent upon the operating system you're working with, it might be Control-C in one for one operating system, or Control-Z for another, or the del character for a different one. But so we needed an abstraction of that. But the important thing is we needed for that signal to get communicated across the network, even if all of the packets were stacked up and there was no room to send another packet. So we had to expand or embellish the basic host-host protocol with this extra capability to communicate interrupts. A different issue is that a lot of these operating systems were provided by the vendors, IBM or Digital Equipment Corporation or whatever company was providing it, and it was not typical from their point of view to allow the users, customers, to get into the operating system to make changes, and yet that was necessary in order to provide access, in order to connect up the imps. We needed a novel, de novo hardware interface, and we needed code inside of the operating system. That caused me to create the terminology network control program that designated that software. Over time, the term host-host protocol was too bland. NCP was a very handy acronym, and it got repurposed into network control protocol to designate what had previously been known as the host-host protocol. And the idea that you had to make an incision into the operating system was widely accepted. No mystery about that, and there was no need to emphasize that with a special term. Next slide. So to summarize in a way, the Arpanet connected a heterogeneous set of computers. They weren't all the same. They didn't come from the same vendors, and there were quite a lot of differences. They were different in not only the hardware, but also even in the way they represented characters. You had different representations for character sets. ASCII didn't become common until just a bit later. IBM used extended binary control, binary encoded interchange called EBCDIC, and there were others. So over time, over the next several years, byte size became standardized, character sets became more standardized, and we had originally used one-way connections with the intent of using a pair of them to set up a connection, and it was decided that was unnecessary, and so every virtual circuit that we created was a two-directional circuit. And so the network control protocol got replaced by the transmission control protocol that Vince Cerf and his team worked on. And that was part of the transition to the internet with the insertion of a layer below TCP called Internet Protocol that connected disparate networks together. So that was the critical thing. But the Arpanet was a homogeneous network from a communications point of view. It had a single vendor. It had a single operator, Bob Brannigan and Internet Operations control room kept track of which imps were up and down, which lines were up and down, and so forth. And it was understood pretty quickly that there would be other networks and that you couldn't have just one network for the entire world. You're going to have a lot of independent networks. And that's what led to the internet and the worldwide impact that we've all experienced. Next slide. One of the things that had not been planned exactly, but in retrospect is not a big surprise, is that the Arpanet project engendered the creation of a community, actually multiple sub-communities as well. There were a number of people who were expert at the software and the protocol side of things and started to help out the next neighbor. So the people who were grad students working in each of the initial sites wound up doing neighborly consulting with other sites as they came on board. The development of hardware interfaces led to a little bit of manufacturing commonality. A couple of companies started to produce interfaces for the small machines. And then there was a much bigger and more important factor of people who were working in networking started to think of themselves as being part of the same community. We had network working group meetings, is what we called the group. When we had 50 people show up, we thought, oh my goodness, this is getting pretty big. And we started to subdivide our meetings into 2 parallel sessions. Over a period of time, that has all morphed into the Internet Engineering Task Force. And now, at least pre-pandemic times, 3 times a year, the meetings have between 1,000 and 2,000 people show up. And left lots and lots, I don't have any idea how many people participate remotely and via working groups online and via mailing lists. Next slide. So the top level of what the Arpanet accomplished was to create a clarity across the world, actually, that networks were feasible. The reactions of the existence of the Arpanet, you could feel it around the world. The French, the British, and the Canadians, for example, all started or had networking projects. I'm particularly fond of the interactions we had with some Canadians who wanted to build a network to connect Canadian universities. I don't think that particular project came to fruition, but eventually, of course, they did connect not only their universities, but everything. But they called their proposed project CamuNet. And if you look at the geography of Canada, most of the population is right along the southern border. You have, or near it, you have Montreal and Toronto and Vancouver and so forth. And even if they're not butt up against the border, they're in the southern part. And but one of the things they perceived right away from a political stance is that they wanted to connect those sites so that data would travel. Their slogan was they wanted their data to travel east-west, not north-south, meaning they didn't want their connectivity to be in the form of send it into the U.S. and then pick it up later and bring it back out. Didn't bother those of us who were working on the Arpanet, but it was just interesting to see the political side of this emerging absolutely from the beginning in the thought process. And there were similar issues in other parts of the world. Another key result, of course, from the Arpanet is that a heterogeneous network, not specific to a particular vendor, was not only possible but had benefits. And that's in contrast to what some of the companies, IBM and Digital Equipment and some other companies tried to do, which was to build proprietary networks that will connect their products together and be more tightly integrated into their operating systems. Those succeeded for a period of time, but were eventually overtaken by the enormous power of having an open network. Another very big thing was the idea that protocols could be layered into, and that you could build on top of the layers. Our focus was that these layers didn't have any specific structure to them, and that they were there more for convenience than for imposition. You could get underneath them if you had to. You could ignore them. You could put layers in between. I was very heavily involved in the early periods. I went off for several years to do other kind of research I was interested in. When I came back and started paying attention to networking, I discovered that the OSI folks had decided that there were exactly 7 layers. I almost fell over laughing and kind of missed the whole point. And if you look at the so-called application layer and you look inside of that, there are a zillion different layers embedded there. So, I don't want to be too negative about the 7-layer model. It's helpful in some respects, but it's not accurate, nor is it, and it's a bit distracting in some respects. Far more important than any of that is that a key thing about the way we worked was that we had an open protocol stack, as I said. We had an open standards process. The documentation was available to anybody, and anybody could participate. Next slide. So those 3 aspects of openness were qualitatively different from the standards process used in the telephone networks, for example, and have made a huge difference in the world. The fact that the specs are available free of charge to anybody, anywhere, anytime, and that participation is open to individuals, not just to governments, not just to big companies, is one of the things that's driven a lot of innovation. Next slide, please. One of the key things that emerged in the transition to the internet is the so-called hourglass model, in which there is a common protocol in the middle, the IP layer, and then a lot of room both above and below that for variation. Next slide. The stuff above is a multiplicity of uses, and the stuff below are a diversity of transmission mechanisms. And you see there radio and Wi-Fi and Ethernet and fiber and coax and etc. And above, you see all kinds of applications. Next slide. And focusing just on the top side of that. Next slide. Here we have HTTP for the web. We have email that got created relatively quickly, SIP for voice and other interactive analog type applications. DNS as a name lookup translation, etc., and whole industries and major companies created around all of these. Next slide, please. The open participation also meant that there wasn't any limitation as to where the contributors would come from. Sometimes I would joke, that in the original Arpanet plan, if you read it very carefully, it says, "Oh yes, and at this point we decide that we're going to have the creation of voice over packet switching, and let's have the Estonians do that." In those days, it probably would have been hard to get very many people to even figure out where Estonia was. And along comes Skype, and all of a sudden long-distance phone calls, which used to be expensive even in the US and enormously expensive internationally, became essentially free. Tremendous disruption and tremendous improvement in many of our lives. Next slide. So I put at the beginning these major forces. Let me say just a few words about that. Next slide. On the technology side, we have 2 things that were happening over a long period of time. One is Moore's Law, which is really an observation of how fast the technology was changing rather than a force that's being applied to it, translates into a factor of 10 improvement in cost performance every 5 years. nothing in human nature has ever changed at that rate. If you look at labor productivity figures, it's a good year if productivity improves, say, 3%. Here we're getting improvement that's measured, qualitatively differently from that. 10 years, a factor of 10 every 5 years is a factor of 100 every 10 years, and over a 40-year period is 100 million. That is an annual rate of return, if you will, of 60% per year. Try getting that on your money. And then that helps from a brute force point of view, and it's certainly one of the key factors that's had an effect on networking. But the other is that we've also spent a lot of time on computer science aspects. Improvement in algorithms, improvement in graphics, improvement in artificial intelligence, speech understanding, etc. Next slide. Here's Moore's law plotted. The axis, the y-axis on the left, those are powers of 10, and then the years are plotted down on the bottom. And then the fine print, and you can't read this very well, but it'll be in the slide deck, are plotting different aspects of the technology: the cost of floppy drives, the cost of big drives, the cost of memory modules, the cost of core memories and flip-flops and so forth. And all of the curves go basically in the same direction. That's roughly linear down and to the right, which is factors of 10 every few years. I thought this is helpful. This is real data, and in the slide, in the notes, I think, is a reference to and credit to the man who put this together, a professor in I think Australia. Next slide. This is just me using the opportunity to make a suggestion. I think it's helpful to have a little bit of technical literacy. The easiest and most enjoyable and shortest suggestion I have is an essay by early 1900s naturalist called J.B.S. Haldane, titled "On Being the Right Size." I haven't been able to pin down the exact publication date, but in early 1920s somewhere, in which he observes that in the animal kingdom, most of the textbooks of his day don't talk about the differences in the sizes of animals, but in fact, size and complexity are very, very closely related to each other. You can't scale a dynamic system up or down without changing it dramatically. And in the case of animals, just relating how much oxygen they have to take in it's related to their body mass, but their ability to do it is related to their surface area. So you get a cube versus square tension, and a number of other things happen. And this happens in all dynamic systems, whether or not we're talking about biological systems or we're talking about man-made systems or computer systems. So if you have time, I recommend it. It's only a few pages long, and it's nice reading. Next slide. Well, technology is good. Human nature, as I said, stays more or less constant, and you can make up your version of the good and the bad, if you like. On the good side, a lot of initiative, a lot of innovation, cooperation, and on the other side, all of the factors that bedevil us in ordinary society come into play in the networking world. Next slide. Economics and market forces also come into play. The ideal is that you've got an open market with everybody able to compete on a level ground. It turns out that in actual real life, particularly on the supply side, nobody likes that. They all try one way or another to gain an unfair advantage. And that's important for stimulating innovation in various ways. Next slide. That's the end of the formal slides. I've taken a few minutes longer than I had hoped to, so I will just pause here and be available for any questions or comments, and delighted to engage in interaction.
Great. Thank you so much, Steve. It's Glenn again. Okay, so I've been inviting people to type in the chat. Let me start off with Alfredo's question. Alfredo, did you want to gain access to audio and elaborate on your question?
Sure. Thank you.
Okay, go ahead.
Thank you, Glenn. This is Alfredo. Thank you, Steve, for the presentation. It was great. I was wondering, back in the 90s, late 90s, I was part of a research project with National Science Foundation, and we were talking about Internet 2, and which is still, as I understand, up and running. So I was wondering, what interaction did you and your team with Arpanet had in innovating and moving forward the Internet 2 project?
Well, we're talking about a pretty. I'm sorry.
No, go ahead.
The big difference in time, the initiation of the Arpanet in the early days of building protocols was in the early 1970s and continuing on. Internet 2 was a good deal later. As I said, it was DARPA that was initiating this network research. In the earliest days, the National Science Foundation's attitude about computers were that these were big machines that supported real science, physicists in particular. And it was several years before they started to engage in supporting computer science research generally and networking as well. When they did get involved, they got involved in a very, very big and important way with the creation of first CSNet and then NSFNet, and then finally, NSFNet became a network of networks with a big NSFNet backbone and a lot of regional networks. And the speeds of the network that they built were based primarily on megabit speeds as opposed to kilobit speeds. Internet 2 was a big leap past that, but by that time, commercial networks also came alive. And so Internet 2, as you said, was started in the 90s, but has coexisted with a much, much bigger commercial footprint. I have not been keeping track closely of Internet 2, although engaged in some interactions from time to time. And they're still pushing forward on certain fronts, particularly to support very high-speed networking for advanced applications in universities. But it's much more specialized than the broad internet. So I don't have a whole lot more to add to it than that.
Great, thank you, Steve. Let me read out Maulud Khalif's question. He's asking, what roles did the French network, the Cyclades, and the British also NSFNet in the development of the internet?
Let me take the British first. Donald Davies and his team at the National Physical Laboratory had pretty much the right ideas, and were trying to build something equivalent, but they didn't have the level of funding that was available in the US. I believe that they are properly credited with introducing the term packet switching. I think Roger Scantlebury interacted with Larry Roberts and others at the Gatlinburg meeting in 1967, as I understand it. I wasn't there, but that's the story I hear. The French work was very interesting along a separate path. Louis Pouzon was at the helm of creating CCLAWS. There's a certain amount of controversy as to what ideas were embedded there and versus what ideas were embedded in the ARPANET and then the internet. I'm not actually, I haven't spent a lot of time sorting out, but they built very credible network. I think the fundamental issue there was that it was sort of focused on being French and limited, and sort of got overtaken by events in Europe as the internet protocols basically won out over in the protocol wars later between the TCP/IP suite and the OSI suite. And so it was, I would say, an important part of history, but I don't know precisely which ideas flowed that one could trace directly back to Cyclops.
Great. Thank you for the answer, Steve. Due to time, I know you have another call within 30 seconds, so I'll have to wrap this up. Thank you again. This was a huge contribution to our body of knowledge, and all of these will be recorded. And thank you, Eduardo, for live streaming to the at-large community today for this session as well. Okay, on behalf of everyone, thank you again for your participation. I hope you can visit and see some of the other sessions that we're going to be doing throughout this module. And again, we appreciate your time and energy today.
Thank you very much, and appreciate the opportunity.
Great. Thanks again, Steve. Bye-bye. Okay, that wraps it up, folks. Thank you again for joining us today. And Steve's rushing off to another meeting. And again, thank you for completing the surveys. We have 17 responded surveys. I'm not sure if people have been watching this session on Facebook as well, but it was an experiment today. And thank you again for attending, and thanks for the questions. And also a special shout out to Lila for finding that resource so quickly, and I converted it to an ebook for you to share. So that is great. And thanks, Joan, for joining us today as well. Alfredo, are you still there? Not sure if he is or not, but if not, well, thanks everybody. We'll see you next week.
Bye to everyone. See you next week with Steve Del Bianco.
Great. Thanks, everyone. Bye-bye.